In our previous session, we have studied the RAT channel and the PRACH and RACH related operation in uplink. But we have some more channels in uplink which we'll have to cover, and then we get on to the next topic. So the channel that we are going to study now is called as PUSCH, Physical Uplink Shared Channel. So what is the purpose of this channel? It carries the data in the uplink direction from the mobile equipments to G-Node B. So in downlink, the equivalent channel that we have was PDSCH, Physical Downlink Shared Channel. Now we have Physical Uplink Shared Channel. And what is the overall PUSCH process that takes place when the data is received from the higher layer, like MAC layer? Once we receive this transport block from the higher layer, your PUSCH does CRC attachments and code block segmentation, and for each block it will attach the CRC, and it is going to use the LDPC coding. There are two types of coding. So we use the LDPC coding for this. Low density parity check coding is what we call as in long term. It's simply an algorithm. Next, rate matching, code block concatenation, and everything. But there is one additional block that is associated with PUSCH, which was not there in PDSCH. What is it? Data or control multiplexing. What is this here? PUSCH not only would be able to carry the data that is coming from the higher layers, it is even capable of carrying, sometimes the control information additionally. Actually, the way that the uplink channels are designed in 5G, there are actually two important uplink channels. One is called as PUSCH, the other one is PUCCH. PUCCH refers to control channel. C here refers to control, which carries some important control information. But uh, the control channel, that whatever we have, whatever the control information it is carrying, it need not be carried only on PUCCH. Sometimes you can carry that control information along with PUSCH also, this channel. Actually, PUSCH is designed for carrying the data. But when you are transmitting PUSCH during exactly the same time, if you have to send some control information in the uplink direction to G-Node B, then they decided that, hey, why we have to use the PUCCH resources and unnecessarily waste them? Why can't we send that information along with the PUSCH itself? So we send that in this PUSCH at this particular place. We add it, we multiplex it. Of course, the receiving entity must be able to differentiate it, remove it out, extract it out, and send. Then only the transport block that is received must be sent to the higher layers. Now the remaining processes are similar. Yeah, yeah. We use the remaining processes are similar to the downlink operation. So we have the scramming mechanism with the help of the scramming sequence. Then we have the modulation mapping as usual, which would identify the modulation symbols, and then followed by uh, the transform precoding. But we already know this transform precoding is an optional thing. We learned that. So it depends on higher layer configuration whether it is getting enabled or not. If it is enabled, then we do the DFT transform precoding. If it is not enabled, we have to ignore this. So DFT symbol conversion won't be there. Directly this modulation symbols would be mapped onto the subcarriers, and then they get converted into the radio signal. We have the layer mapping and the precoding. All that goes out. Resource element mapping, and then finally the OFDM signal generation. But the kind of OFDM signal that we generate for uplink is called as a DFTS OFDM. But one important difference that you observe here is uplink operation is single code word based. So you cannot generate like two code words, only a single code word. But layers, you can map it to up to 4 layers for uplink operation. You remember we have downlink, two code words and up to 8 layers we could create. But in uplink, we can create up to, we can have up to 4 layers. Now, what are the additional symbols that you would attach and send when you are transmitting this PUSCH? So you have the DMRS that's going to go in like before pre-coding. We have to insert these DMRS symbols. They also will go through the same channel impact process as PUSCH. This is similar to PDSCH. But in uplink, we have something called as a SRS, sounding reference signal. We don't have CSARS. CSRS is kind of a downlink reference signal. Sounding reference signal is uplink one. So we have two different types of reference signals. GNODB transmits CSARS to the mobile, and mobile transmits sounding reference signal to the GNODB. So it's the way. But again, both of them would be used in two different circumstances, which anyway we will see little later. But again, these sounding reference signals that whatever the mobile equipment transmits need not be pre-coded, but they'll definitely occupy some resource elements. So you, whatever the recognized resource element positions are there for SRS, you will place them, and then after that you generate the OFDM signal and then transmit. So if you take a look at this left-hand side box of PUSCH channel, so this is the kind of activity that would be taking place. Your transport block CRC size attachment is 24 bits or 16 bits. It would be decided based on the total size of the transport block arriving. If it is bigger than 3824 bits, it is going to be 24-bit CRC attached, otherwise 16-bit CRC would be attached. But once it is sent to the next box, You are using LDPC coding. By using the LDPC block sizes, so you do the division depending on which base graph has been chosen. This is again configured. So you divide the higher layer data into multiple small pieces, and for each piece of it, you are going to attach a 24-bit CRC for separate uh, identification. Then we have the channel coding, rate matching and interleaving, code block concatenation, all those things would take place. At the end, we are going to have this multiplexing part where you are actually multiplexing something called as UCI. On the basis of the configuration, UCI stands for uplink control information. So you would be sending the uplink control information and HARC acknowledgements and negative acknowledgements, are basically HARC acts, or CSI information. Even CSI is also considered as uplink control information. CSI here stands for channel state information, the one that we have studied for my mode beamforming. Pre-coding matrix indicator and rank indicator related things. All right, next. So once all of it is done, then you are going to have the code word generated. That would go through normally the scrambling process, the same as the ones that we have studied earlier. Now this scrambling mechanism is different for the UCI placeholder bits, nothing but the control information that we are multiplexing. For that, the scrambling process is different. Uh, you know, and for the actual data part, the scrambling process is different. For the actual data part, you would be taking each and every bit of the data that is generated out of the transport block, and you do the modulo operation with the scrambling sequence. Scrambling sequence calculated with this CINIT value, where NRNTA will play an important role. So there is a special case called as message A transmission on the PUSH, which is as part of the random access procedure we have studied. We have seen this thing called as message A. We have two types of random access procedures, two-step random access procedure, four-step. In our previous session, we have understood that. In two-step random access procedure, the message that we send is called as message A. So when you are transmitting message A, then the RNTA that you have to use is this: NRNTA into 2 to the power of 16, N wrap ID into 2 to the power of 10. So here, so there is an additional element here that is being considered here is called as wrap ID, random access preamble ID. So the whatever the random access preamble ID mobile equipment is using, along with while sending the message A, message A, if you remember, would be sent together. Like we are sending preamble preamble on the PRA channel. At the same time, we are sending the data also on the PUSCH by using the resources. Whatever preamble number that you are using to transmit the preamble to generate the Jadov-Chow preamble sequence, that preamble number would be kept here as the CINIT. Obviously, once the GNODB receives the preamble and the message A, the idea is that if preamble is corrupted or something happened to the preamble, if GNODB would not be able to estimate the received preamble correctly for whatever reason, then obviously GNODB won't have the CINIT available. If GNODB did not have the CINIT available, because it failed to guess the received wrap ID, the receiving GNODB would not be able to decode the PUSCH data that is arriving and carrying this message A. It won't be able to decode. That means that if there is a preamble failure in this two-step random access procedure, when you are sending preamble plus the higher layer message, we call it as message 3. If we send them together, we term it as message A, all of these two things together. So the idea is if the preamble reception is a failure, you don't bother or you don't care about the uh, your message A that you are transmitting. So we expect even that to fail when your preamble reception fails. So that is why they have linked these two things together. So that's why the C init value, which is used in calculating the scrambling sequence, so have linked to this. But you don't require that uh, ID part if you are transmitting PUSH normally. When you are doing normal PUSH transmission, not used for this random access procedure preamble, random access procedure related thing. So in normal cases, the C unit value would be NRNTA into 2 to the power of 15 plus NID. Simply whatever the RNTA that is allocated to you, and then based on that you do this. But if you are generating the C unit for message transmission, the NRNTA is nothing but the RA-RNTA that is computed by the mobile by using by using which resource you are transmitting the period channel. On the basis of it, you calculate this RA-RNTA, in which slot you are transmitting, which frequency resource you are transmitting, which subframe you are transmitting. All those numbers would be used in calculating this RA-RNTA. We have studied that. That would be used as NRNTA here. But in case of uh, in case of PUSCH, normal transmission, when the mobile is in connected state, definitely mobile equipment have been already associated with a RNTA. So that RNTA would be used. That RNTA would be used for uh, calculating the C unit value. And what is this NID? NID would be either your network ID. Typically, it is your PCI, physical scrambling code, or there is a separate message related data scrambling index or data scrambling identity that can be used for PUSCH. It is provided as part of the higher layer parameters, either in the form of for message case you will be receiving it as part of the SIB message data scrambling index, or if the mobile is using the genuine PUSCH, that time mobile might get this data scrambling identity PUSCH. If none of these two things are available, then you have to use your NID itself as it is, the physical cell ID or N cell ID. You would be using, substituting into this particular position. Ultimately, you calculate the required C in it, and then from that, you will be able to generate the scrambling sequence, use that scrambling sequence to scramble the data. But when for the UCI placeholder bits, uh, there are placeholder bits are basically considered as X and Y here. What is X, what is Y is depending on different types of data. If it is X type of data, in that position, you always need to have, if BQI input bit is X, input bits are X, all output bits will be set to 1. B tilde Q of I is the output bit must be set to 1. Otherwise, if it is Y kind of bits, then uh, the output bit is equal to the the uh, previous bit of the BQ of I. So it is like that. But it is some way of scrambling the data, which obviously is known to both mobile equipment and GNODB. They will be able to descramble it. Especially in case of UCI, there is a special way of scrambling. But for data part, you scramble with the normal mechanism. Whatever this additional data that you are multiplexing onto this PUSCA channel, when it is multiplexed with these coding information, the additional uplink control related data, even for that we have to apply the, like channel coding. So there are some patterns identified where you will be placing this, X and Y here, what kind of a control information you're packing, and how you are going to do the channel coding operation when especially when it is very small amount of data that you are packaging and sending. For example, you can see that X is getting repeated when there are, if your if your small block length is only 2 bits, for example, you generate the third bit C of 2 with the C0 and C1 modulo 2, and then how do we place it, depending on your modulation technique. If your modulation technique is QPSK, so BPSK, etc. In different cases, how do you transmit that? Because it is 3 bits, the 3 bits would be sent like this: two original bits plus 1 bit additionally generated. But if it is modulation is 2, now it you have to prepare 6 bits. So you will be sending 6 bits like this: CO, C1, C2, the original 2 bits and the generated C2 bit, and then again repeat them. If your modulation is increasing, so you're going to place these XXXX, YYYY here, or XS and here, which is like a kind of repetition, the placeholder bits repetition. We don't bother much. Anyway, when you are implementing, you will realize if you have to really implement. So I would kind of ignore this part for you. Okay, why it is needed. I will send the information though anyway in PPT. If you want to use it for your future purposes, you can use it. Okay. PUSCH modulation, just like PDSCH, can be dynamically decided on the basis of the mobile equipment CQI indicated situation. If mobile reported good CQI, then it would be decided to be higher modulation technique. Otherwise, it is decided to be lower modulation levels. But some mobiles may not even be able to support transmitting at 256 QAM until and unless they are really powerful mobiles. Because when the modulation technique keeps getting advanced, the complexity of the device will be higher. So mobile equipment in order to easily send the information, so it need to have huge amount of processing power and capabilities. It need to have. But anyway, mobile during radio connection, typically it would report to the network about what are its capabilities, including the modulation capability, what modulation technique it supports. For example, whether it supports 256 QAM or not. Most of the mobiles typically support up to 64 QAM if you are using, a good enough mobile phone for both uplink and downlink. Especially, there is a probability where mobile equipment may support 256 QAM for downlink, but it may not support 256 QAM for uplink. So that means downlink receiving is much little easier when you compare with uplink. So when these mobile has reported its capabilities, network kind of takes that into consideration. On the basis of that, it would be configuring the required modulation and also based on the network conditions. Okay, now there are again now two cases. In transform precoding in disabled case, you won't be using this pi by 2 BPSK we have studied. But if transform precoding is enabled, then there is an option available for pi by 2 BPSK also. First of all, what is the purpose of transform precoding enabling? If you are enabling transform precoding for any subscriber, the literal meaning is that we wanted to save the battery power by decreasing There seems to be people leaving. What happened? Hello?
So
Can
now
someone hear?
you are
Yeah.
audible now.
How much time I have been lost?
Sir, around 1 minute.
2 minutes.
1 minute. Okay. Should have been some issue on the network side. I don't think there is any problem on my side. Everything looks good. But why did you report it? You can report it by using your chat box, right? You could have reported it when you thought that it is missing. Please do that, guys, next time because I won't know. I'm continuously speaking, and that too, you guys are not asking questions and not being so much interactive. It'll be tough for me to guess that you are not able to listen to me. Okay, so please report it immediately if you can't listen to me on the chat box. Okay, I hope now it is clear. How much part I have to repeat? This whole slide you have missed it. Can someone confirm that? I'll repeat on the basis of that.
Yes, sir, you are audible till you have explained now why this transform recording is used till that part.
Yeah. Okay. Okay. I'll continue from there. So transform precoding is used to reduce the power level of the subscriber by decreasing the PAPR, peak to average power ratio. Now, if transform precoding is getting enabled for any subscriber, definitely subscriber is facing some power related problems. Otherwise, transform precoding would have been disabled. But if it is enabled means subscriber is facing issues related to transform precoding, related to power, uplink power related things. So they thought that if the mobile is facing the issue in uplink power related thing, we are enabling transform precoding to reduce the PAPR so that mobile can transmit it with less power. Good. Along with that, we have to do some additional thing also. Not only we should allow the subscriber to use QPSK 16 QAM, 64 QAM, and 256 QAM, but we also should give the chance to the mobile equipment to use BPSK, with which you would be getting very less data rate, obviously, which is because it can only send 1 bit per symbol. It cannot send more than 1 bit per symbol. Data rate is drastically reduced, but at the same time, it will be better for your overall operation because you will be able to use very, very less power to transmit a BPSK signal compared to QPSK or any other thing. But definitely data rate is down. But why are we using 5 by 2 BPSK? Why are we not using normal BPSK? Typically, normal BPSK is used for common channel related modulations. In order to segregate between common channel modulated symbols and PUSH modulated symbols, they decided to use this special 5 by 2 BPSK for this PUSH. But anyhow, in this 5 by 2 BPSK also, the two uh, constellation points are just differed by 90 degrees. So that is why we are calling it as 5 by 2 BPSK. It is little different from normal BPSK. Now, transform precoding is enabled. Mobile is having this additional option of using 5 by 2 BPSK. Doesn't mean that it is mandatory. Even if transform precoding is enabled, mobile can still be using QPSK 16 QAM, 64 QAM, etc. It depends on channel conditions. If mobile is facing power problem, at the same time mobile is facing the CQA issue as well, then definitely you would be going for 5 by 2 BPSK. You are very far away and signal strength operations are very bad and everything like that. Otherwise, you would be using higher modulations. But when the transform precoding is disabled, mobile is not required to use 5 by 2 BPSK because it's not facing any power related issues. So we are not worried about PAPR or the DFT symbols. So obviously the mobile would get a chance to use only these modulation techniques. Okay. Okay, not much to see here. PUSH, where you can actually from one code word you can form 4 layers. So Uh, if it is one layer, it is as it is. If it is two layers, it is a halfway split. All even number symbols would go into one layer, odd number symbols would go into another layer. If it is three layers, three-way split, 3i, 3i plus 1 and 3i plus 2 symbols. That means like you have 0, 3, 6, all will be grouped as one. 1, 4, 7 would be grouped as one, like that. So 2, 5, 8 would be grouped as other. Otherwise, 4 by 4, 4 case split, 4-way split. Whatever the available symbols are there, you are dividing them to make form that multiple number of layers. Again, so how many layers are required? All that will be dependent on the network conditions and so on. The pre-coding matrix indicators and all the other factors will play in a role, your channel estimations. Transform pre-coding is converting these symbols, whatever the symbols that we have, these are the PUSCH symbols, your transform pre-coding. So this is the DFT operation to convert it into DFT symbols. Rest of the part ignore. I've decided not to go in depth because there were complaints that it is too in depth. So we ignore this part. But there is one thing that we have to recognize related to the PUSCH resource allocation related technique. The number of resource blocks that are allocated to PUSCH must be following this particular rule: 2 to the power of alpha 2, 3 to the power of alpha 3, 5 to the power of alpha 5. Number of resource blocks that are allocated for PUSCH operation, uplink channel operation. Here, alpha 2, alpha 3, and alpha 5 are a set of non-negative integer values. Now, how this mechanism works? How many resource blocks are allowed? For example, by looking at this, can anyone of you tell me allocating 13 resource blocks for the mobile equipment for its PUSCH operation is allowed or not allowed? Please participate, guys. I was given a complaint that there is no participation at all from the students. Okay, now I am forced to do it. Okay, now I expect an answer from at least 5 of you. I have 13 resource blocks. Now, can I have 13 resource blocks allocated or not? One answer I got as no,
No.
no. Another answer. Who feel yes? It's possible. Okay. Again, no response. Answer is no. Shagun, yes. Okay, how do you think it is yes? We have to see different answer.
So how can we are not able to allocate 13 RBs?
Okay. So that's where your mathematics comes into the play here. So look at the rule. Alpha 2, alpha 3, alpha 5 are a set of non-negative integer values. What are the meaning of non-negative integers? Starting from 0 and upwards are called as non-negative integers. So you are not allowed to use negative numbers. So 0, 1, 2, 3, 4, any numbers you can use. There is no restriction there. It depending on the total number of resource blocks. Fine. Let us take, we substitute 0 in everything. If you substitute 0 in everything, 2 to the power of 0, 3 to the power of 0, 5 to the power of 0, that becomes 2 to the power of 0 is 1, 3 to the power of 0 is 1, 5 to the power of 0 is 1. So all of them would turn out to be 1. So that means that the number of resource blocks allocated for PUSCH operation is equal to 1. But now, I wanted to get 13. By substituting what numbers in alpha 2, alpha 3, alpha 5 position, we can get 13. That is what we have to look. With some value, we have to get 13. Now, whatever you do, you will never be able to get 13 with this multiplication of it. For example, if you take 2 to the power of 1, 3 to the power of 1, and 5 to the power of 1, all of them would be like multiplied 2 into 3 into 5, because 2 to the power of 1 is 2, 3 to the power of 1 is 3, 5 to the power of 1 is 5. So you just have to multiply them. 2 into 3 into 5, 2 into 3, 6, 6 into 5, 30. So you got 30 resource blocks allocated. It is representing a value 30. For example, if you substitute alpha 5 as 0, alpha 2 and alpha 3 as 1 and 1, so it becomes 2 to the power of 1 and 3 to the power of 1, which is just 6 resource blocks. That means in an indirect way of, a direct way of telling it, the number of resource blocks that you can allocate, that number must be a multiple of either 2, 3, or 5. Then only it is we are possible to reach that number. It should be at least a multiple of all, at least one of these elements. 13 is not. 13 you can't divide with 2. No, it can be done with 3, 5, nothing. So obviously you won't be able to reach with 13 with any combination of alpha 2, alpha 3, alpha 5. So that kind of an allocation is not allowed. That is the point. So
So,
simple.
sir,
Yeah,
so
go ahead.
so that means we are not able to allocate odd number of RBs in case of
No, it
PUSCH.
is not hard. 15 you can allocate, right? For example, you
Okay,
substitute
5 and
0 in
3.
alpha 2 and 1 and 1, 3 into 5, 15. It is not about odd. It is about the number that you can reach with by substituting and by making them by keeping some powers here. That's it. For example,
Okay.
17 you can never reach. Prime numbers are out of scope basically.
Uh, okay,
Of course,
17,
other than 2,
19.
3, 5, yes. 17, 19, all these things you can reach. 16 you can reach. In order to reach 16, you just have to substitute 2 to the power of 4. Remaining
4.
two things would become 0,
0.
like that.
Okay, sir.
So basically there is a rule that this is how we must allocate the number of resources for PUSH. Which resources are allocated, which resource blocks are allocated, that will be conveyed to the mobile as part of the DCA information in the form of downlink control information with this mechanism called as frequency domain resources and time domain resources. Time domain resources would tell you about the slots, are how many symbols in the slot, but frequency domain resources would tell you how many resource blocks in the frequency domain. But those resource blocks must be following this rule. Pre-coding. So you have some number of layers, V1, V minus 1 number of layers. They must be converted into PP minus 1 number of antennas. Your antennas can be many more. Your layers can only be end up having would be 4. Antennas can be 8. Antennas can be 16. Like depending on what you wanted to achieve. For example, if you wanted to achieve beam forming for these 4 layers, you can use. But of course, having that many antennas on the mobile equipment is typically not an ideal case. Even when you are using 4 layers, normally your mobile equipment will have only maximum 4 antennas. And it was told to me that in your Reliance case, you don't have to worry about uplink. You are using a single layer transmission in uplink. So that means that one code word and one layer. So now, how many antennas maximum? If a mobile equipment is operating on 4x4 in downlink scenario, that means that there are 4 antennas available for the mobile equipment to receive the downlink. The same 4 antennas, it can use it for uplink operation as well, whatever the 4 antennas it is having. So the obvious way of doing the pre-coding, is by simply taking the one layer, you have to use the matrix in such a way that the split must happen for 4 antennas. Even if you are transmitting it with 4 antennas in uplink, maybe to form a beam, you are doing that. So this W would become a beam-based thing. So you are choosing the W in such a way to form a beam. That means whatever the values that are placed in this W would do, the angular modification for the Y values or your symbols in a digital way. We call that as digital beamforming. So that means mobile is trying to target to send the data in a beam kind of shape towards the G node B. So idea is that if it is transmitted in a directional way by applying the theta values perfectly, if you try to target to send your beam in a particular direction towards G node B, what happens? You would be basically reducing interference other sides to the other sides of, at least for the other subscribers, or maybe at least towards other cells. Because you are targeting it to send it towards one particular direction, like towards the G node B direction, for example. If you are not even doing beamforming, simply if you are performing something called as transmit diversity, basically by using some special transmit diversity based matrices, you will be just transmitting them onto these antennas. The same signals would be transmitted on all the antennas, but by applying uh, transmit diversity. Transmit diversity basically will increase your SANR or SNR, signal to noise ratio, which will make the receiving antenna to receive it cleanly. Okay. So the W size is going to be P into V. So output would be P and input is V. So W must be P into V. For example, if this is 1, you want it to be transmitted on 4 antennas. We want to use a 4x1 matrix so that we can convert to one stream into 4 units, which can be transmitted on 4 different antennas. Now, we have this concept of virtual resource blocks and physical resource blocks and interleaving and non-interleaving in uplink as well, just like downlink. What happens here in this particular scenario? If required, mobile equipment is asked to transmit the data not in contiguous resource blocks, but in like resource blocks in different frequency locations in your frequency domain. So all the subcarriers won't be contiguous, or all the resource blocks won't be contiguous. Contiguous means one next to the other. There would be a distance between them. You have one resource block here, one resource block there. Again, what is the reason? If a particular frequency is faded in the uplink direction when you are transmitting the data, only one subscriber won't be impacted. Instead, all the subscribers would be impacted equally, or whatever the problem that is present in the network is shared by all the subscribers equally instead of one guy facing the burnt. So that's the purpose of this virtual resource blocks and physical resource blocks, where you would be performing something called as frequency hopping by doing this. If there is no interleaving, direct it is. If it is interleaving, then you have to identify exactly in which resource blocks you have to transmit the symbols that you have converted into virtual resource blocks, virtual RBs. You'll be placing them onto different physical resource blocks and then generate the signal. Okay. So that is all we have for PUSCH. Now the next channel that we have to see is PUCCH, physical uplink control channel. What is the purpose of this? As the name itself suggests, it is to carry some control information in uplink direction. What kind of control information it would carry? It would carry ACK or NAC. It would be able to carry ACK or NAC either only for a code word or for code block group. What is it? I'll show you. But it can carry ACKs and NACs for the data that is received in the downlink direction. You will be transmitting the acknowledgement or negative acknowledgement in uplink. Remember, we have this ARC process. This ARC mechanism is kind of required in both uplink as well as in downlink direction. But the concept in uplink and downlink differs a little bit. So how it differs? What kind of logic goes into it? So we have the G-Node B, we have the mobile phone. If the G-Node B is sending the data in downlink direction on this channel called as PUSCH, so you are getting a transport block on it, along with the CRCs added, etc. Now you try to find out whether this PUSCH transport block you have received is accurate or not. And if you find that this transport block is successfully received, you have to send the ARC acknowledgements or negative acknowledgements in uplink direction. You would be reporting it, ACK or NAC. If you are reporting a ACK, you are reporting to G-Node B that it is well and good, you can continue with the next one. But if you're reporting a NAC, you are basically demanding the G-Node B to retransmit that. So this is the downlink related ACK-NAC operation, and this ACK-NAC is supposed to be sent on this UCI, uplink control information, on this PUCCH channel, physical uplink control channel. So this is applicable for data arriving in downlink and ACK or NAC going in uplink direction. Here it would be exclusively signaled in this particular case in the form of ACK or NAC. But what about the uplink scenario? Mobile equipment, and we have G-Node B. Mobile transmits this data on this particular channel called as PUSCH, the one that we have just now studied. So transport block received from the higher layers, processed, added with all the CRCs, everything sent out. But once received by the G-Node B, process that, find out the CRC is matching or not, or indirectly it will be able to find out whether this particular PUSCH transport block corrupted or not corrupted while getting transmitted. Now, what if this is corrupted? How does the G-Node B need to report this to the mobile if it is corrupted and requesting for a retransmission? In downlink, they have decided not to use this ACK-NAC format directly on some particular channel. Instead, once the G-Node B detects or decides that the PUSCH transport block is kind of failed, its CRC is erroneous and we could not solve the errors with the help of the coded bits, G-Node B definitely need to ask mobile equipment to request for the retransmit or mobile equipment to do a retransmission. So instead of sending ACK or NAC, what does G-Node B do is it will send the downlink control information to the mobile. In the downlink control information, G-Node B will again configure PUSCH resources for the subscriber, PUSCH resource blocks. Along with that, it will give an indication in the DCA itself whether the PUSCH that it is allotting is actually for the New transmission or retransmission? New or re, it will convey. So there is no separate, like it is getting carried on some special channel, like in this case PUCCH. It's coming along with the DCI. If you get such an instruction that, hey, the PUSCH that you transmitted is failed, I'm reallocating you PUSCH resources, you are supposed to retransmit the transport block once again. Don't go for new transport block preparation. I'm not expecting new transport block from your side at this particular point in time. I'm expecting the same thing that I have received earlier because it failed. Maybe GNODB can ask mobile equipment to send a different redundancy version if required as part of incremental redundancy procedure. So two different mechanisms, but in both directions, in uplink or downlink, definitely this ACK acknowledgements and negative acknowledgements are a common practice. But in what way we are intelligently giving the information is different. In uplink, it is straightforward. It would be called as ACK, but in downlink, it is the hint would be placed inside the DCI. Okay, next. Scheduling request. So this PUCCH can carry scheduling request. Scheduling request is a way of requesting for the resources in uplink direction on this particular channel called as PUCCH. You can request for uplink resources. So to request that, what is it? I will explain. Now, the third category of information that can be carried on PUCCH, CSI, channel state information. CSI is basically mobile equipment's estimation about the channel conditions. But which channel is the question? So you can ask the mobile equipment to estimate the channel conditions on the basis of SSB that is received by the mobile or CSI RS that is received by the mobile. Which one is better? Is it better for GNODB to ask mobile equipment to measure the channel state conditions on SSB block, SS block, or special symbols called as CSI RS symbols that are transmitted in downlink direction? Which one is better? SSB is kind of obvious. It is going to be transmitted mostly all the time, continuously. Mobile equipment can easily find out what is the signal strength it is getting on these SSB channel blocks, and on the basis of it can send the CSI report. The advantage of using SSB based channel state information is there won't be any overhead. Basically, that is going to be kind of an advantage for you. What do I mean by the overhead here? If you are using CSI RS, definitely sources for CSI RS in the downlink direction. CSI RS is channel state information specific reference signals transmitted by GNODB in downlink. For that, you need to reserve some resources, need to reserve some symbol positions in time domain and frequency domain. So that is wastage. Instead of it, you could actually send the data. If mobile equipment is kind of capable of estimating the channel state conditions on the basis of SSB itself. But the problem with SSB is, as it is located in you, if you take your entire bandwidth, your SSB is typically located in one particular place. But normally, if you consider it as it is placed at the starting of the band, it is placed at the starting of the band. But if you measure the CSI on the basis of this small bandwidth of radio frequency signal, and on the basis of it, if you estimate the channel state information, it may not be quite accurate. Whatever the CSI information mobile is reporting may not be perfectly accurate. It is not like up to the mark. Why you are not estimating the CSI on the basis of the total band, total signal that you are receiving in downlink? Only small part of it you are measuring. So that's the disadvantage with SSB. So what are the advantages and disadvantages of CSIRS based channel state information? First, advantage, CSIRS can spread to the entire bandwidth. Our network GNODB can decide if it wants to mobile equipment to measure the CSI conditions of a particular subband. It can provide that subband specific information to the mobile. Tell the mobile that, hey, I'm sending you the CSIRS symbols in this much amount of subband. Now I'm expecting your channel state information for for the entirety of this subband. The subband can be anything. It could be half of the bandwidth part. It could be the full bandwidth part. But typically, you ask it for maximum for the bandwidth part. Even network can ask mobile equipment to report this CSI conditions for all the bandwidth parts also, to find out mobile should be placed on which bandwidth part. You can change that as well. So that kind of an advantage would be there in this CSIRS, because it's specially designed to request one particular subscriber to send the CSI information. Obviously, disadvantage is the wastage of resources, because you have to reserve some symbols for that, along with your downlink PDSCH traffic, downlink PDSCH channel. Some symbols would be occupied by the CSIRS special symbols, like your QPSK symbols calculated with the scrambling sequence. So what are the things that mobile equipment can estimate as part of CSIR? Which parameters we typically call as CSI? So these listed ones. You have channel quality indicator, CQI. We see the CQI values, etc. in MAC layer once again, because it's linked to MAC layer. We'll see a lot of things again in MAC layer. That time I'll introduce the tables applicable for the CQI and so on. But what is the CQI value? If you are reporting a CQI value, if mobile equipment is reporting a CQI value, indirectly it would be asking mobile equipment about what modulation and what coding rate it can use. It is kind of suggesting the network about it by reporting the CQI. So each and every CQI value is typically associated with this modulation scheme possible for that particular CQI value and what is the coding rate. It kind of have a link. We'll see that linking later. Pre-coding matrix indicator, which we know already from our MIMO class, MIMO session. So singular value decomposition, whatever the V is there for the V transpose calculated from the SVD, that V value is typically, we call it as pre-coding matrix indicator. Next, CRI. CSIRS resource indicator. This is kind of giving a hint from mobile equipment to GNODB about which downlink beam is looking good for him. Mobile equipment is reporting. If there are multiple beams on which the CSI is being sent, mobile equipment may be receiving the signal strength from multiple beams in a location. Maybe from one beam, it might be receiving a good signal strength. Other beams, it might be receiving lesser signal strength. But mobile kind of can estimate which downlink beam is better. So it is indirectly reporting on which beam it would like to receive the downlink traffic. Indirectly, it's giving a hint to the network. Next one is also beam related. This is SS block beam indicator. Which SS block is better for you? You are reporting. You remember we have studied at the time of SS block. Blocks will be numbered, indexed, like 0, 1, 2, 3, 4, 5, 6, 7, 8. Number of blocks repeated in one burst. time SS burst. So from that block index, you will be indicating a value in this SSBRI. So what SS beam is better for you? You may ask, hey, what is the difference between the SS beams and your individual data transmission beams? Yes, there is difference. SS beams kind of, if you take a transmitter, SS beam kind of their directions kind of would be fixed. They won't be changing. Now, if, for example, a subscriber is here, a subscriber will have to either choose this beam or this beam. For subscriber basis, we won't be changing the SS beams. They are created for the purpose of all the subscribers that are located that are present in the cell. Now, mobile equipment will have to kind of choose when it is in the middle. It will have to either choose this beam or this beam. It will have to go for a compromise, even though it is in the middle. Because there is no direct beam that is coming towards you. So both these things would give you equal kind of strength, but one might give you little higher. Whichever is giving you little higher, that thing you will indicate. But on the other hand, the CSIRS beam or the CSIRS, the CSIRS always travels with the PDSH. We have studied that already. When it is traveling with the PDSH is this particular user's PDSH. So that time, you can actually target to send the beam for the subscriber exactly towards the subscriber. You don't need to send it to, tentative locations. Little here, little there, not required. You can direct it towards the mobile. That's possible. Because to detect that, mobile kind of giving the channel state information and all that, lot of other details it would be sending to the network. By using all those things, network can kind of estimate like what are the exact angular changes that we have to do for the signal to send this dedicated PDSH towards the subscriber instead of sending here there. But SSBRI, your SS blocks, you will decide it on day one. What and all directions you have to send it, and they kind of keep constant directions. But when it comes to these PDSH, they are directional. They are more directional than SS blocks. So to indicate these two different things, so we have two different indicators here on the CSI. Layer indicator. Layer indicator is deciding how many layers you are asking the other guy to transmit. So that either increases or decreases your data rate. If there is a suggestion to increase the LI, then obviously data rate would increase because you would be taking more number of symbols, more number of data from the transport block as a transport block, process it, and generate more number of symbols and divide them across layers, and then multiply that with the pre-coding matrix indicator. Then you transmit that on the antennas. But this layer indicator is not a direct field. It is actually kind of calculated on the basis of the other things in place like PMI, CRI. So there is again a linking mechanism, LI to the other fields. Even rank indicator also, I have explained you, rank indicator is mathematically speaking, rank indicator is how many non-zero diagonal elements we have on the main diagonal matrix and your SVD. That is what we are calling it as rank indicator. That kind of telling how much effective your MIMO is. You are reporting it. If you are reporting a bad rank indicator, that means that MIMO conditions are not good. Another equivalent to that is actually called as RSRP, reference signal received power. If your reference signal received power is good, typically your MIMO channel would be in a better condition. Your rank indicator would be high. Like they are like near to each other. This whether you are reporting it in the form of RSRP or rack indicator is similar. But sometimes you are asked to exclusively report RSRP, received reference signal received power, or sometimes you are exclusively requested for reporting rank indicator. So whatever is configured and requested to be reported, you report it. As we have already seen, so this whole package, these three pieces of information, the control information, is carried either on the PU-CCH channel or PU-SCH. It's kind of not mandatory to be sent on PU-CCH. But when you are carrying it on PU-SCH, you cannot send it with scheduling request. Because you are already, if you are using PU-SCH means already resources are available for you. Now you should not need to complain about resources once again by sending scheduling request. So out of these three packages, scheduling request is not allowed to be sent in when you are sending in on this control information on PU-SCH. The other things, yes, you can send. Other two things, ACNAX and CQI or CSI information. Okay. While you are sending this UCI on the PU-CCH, you can send it in different combinations, as you can see it over there. You can only send HARC ACNAC. You can only send scheduling request. You could send HARC ACNAC plus scheduling request. Or you can send CSI only. Or you can send CSI plus SR. CSI plus scheduling request. Or you could send HARC ACNAC plus CSI. HARC ACNAC plus CSI plus SR. Combinations, depending on what was requested from the network and what mobile would like to send. So you would be choosing the corresponding combination, prepare the number of bits of data. Of course, the sizes are specified for each and every type of data in different scenarios. The sizes are flexible. They are not like kind of fixed. They are variable. In some cases it is fixed, some cases it is variable. Mostly the HARC ACNAC and scheduling request are fixed size. CSI information is very highly variable, the CSI information, because the number of parameters the network can ask you to report will vary, as there are 6 different type of mechanisms that are present here, to which are asked to be reported. So now, depending on how much amount of traffic you are sending, how much data you are sending in different conditions, one corresponding PU-CCH format would be decided, which is present in the table that is listed here. Now you can see each format supporting how many number of bits for PU-CCH or how many number of symbols it can transmit and how many bits it can carry. So number of bits and number of symbols are same. That kind of gives us already a hint that PU-CCH uses BPSK modulation. It tells us already. Because the number of bits are less than or equal to 2, number of symbols are 1 to 2. So similarly, there are other combinations also. We don't bother much on those combinations here right now, because not coming into the L2 part. So decided to ignore going into the deeper details there. Okay. First, we are going to have a look at this HARC ACNAC. Now you can report HARC ACNAC with 1 bit per code word in each carrier. For each carrier. We are ignoring multi-carrier cases. Right now, we are going to take single carrier. But what is the meaning of code word? Code word is generated after processing your transport block. But we are sending HARC ACNAC for downlink. Downlink data is arriving, you are sending ARC ACNAC in uplink. But while you are receiving the data in downlink, maximum you can receive up to 2 code words from the G node B. That's how it is configured. So if network has asked you to report ACNAC for code word level ACNAC, you would be using simply 1 bit information. That 1 bit will represent either ACK or NAC, finished. If there are 2 code words, you require 2 bits. If there are 2 code words to report your ARC ACNAC. Otherwise, it is single bit. If it is 1 code word. Next. Network might also ask you to report this ARC ACNAC for code block group as well. What is this code block group? If you remember, transport block, we first add CRC, later it will be divided into blocks of data, especially when the transport block size is heavy. We divide it into pieces. So after dividing that into pieces, for each one of those blocks of data, we are attaching CRC. Network kind of creates this kind of a block group configuration. A block group can be containing 2 blocks in it, or 3 blocks in it, or 1 block in it. So different configurations are possible based on the higher layer parameters. But mobile equipment would know how many blocks together should be considered as a block group. Now you would be sending a ACNAC for these groups also, code block groups as well. So you received the data, you received a code word. Inside the code word, you started finding out how many blocks of data is present, how many CRCs are present. Now you will kind of detect and identify which block CRCs have actually failed instead of reporting it for the entire code word. This was not there in the old technologies, kind of invented in the new, or introduced in only 5G, or not there in 4G, completely in the earlier versions. What is the advantage of reporting block level CRC, say ACNAC? If you report that one particular block of data is failed or corrupted with the help of those CRCs, you detected that. There are 2 CRCs that are failed. Block level CRC failed. Your transport block level CRC failed. Because the data that is present inside, if the data is corrupted, this block level thing would fail. Maybe one block group related specific data failed. This you detected with the help of these additional CRCs attached. That means that this transport block CRC failed because of this particular block group. This transport block group. This is successfully received, this is successfully received, this is successfully received, this is successfully received. We try to solve the errors of this block group because for each block, there is coded bits attached. For each block. With the help of the coded bits, we try to solve the errors here. But if the errors are solved, well and good. But if the errors are not solved, in the old techniques, you report that the transport block reception is failed, you ask for the entire transport block to be retransmitted. But they have upgraded that mechanism and they said that, hey, if you can ask the mobile equipment to report only which block group is failing, only that block group itself we can retransmit instead of retransmitting the entire transport block, which will again waste the resources because a lot of pieces in the transport block are successfully received. Their CRC is matched. Only one block group CRC failed. So that means now the transmitting ARC mechanism have to maintain not only the transport block in its buffer till it receives an acknowledgement, but it also need to maintain these transport blocks. I'm talking about the transmitting guy. So there are 2 guys. You have the ARC process. Assume that this is the transmitting ARC. So this guy will have a buffer to store the things. Transport block arrived, processed, and converted into he added all these things and converted into code word. But at this particular stage, what happens is you maintain all these code blocks. Okay, so along with their CRCs and everything, you maintain them in your buffer. This is on the transmitting side. You transmit it, receiver, which is the mobile in this case, receives it. Identify which block is having the CRC errors or failed by reporting a NAC. And also transport block is NAC. And individually block group level also there is a NAC. Once you reported the NAC, by taking it from the buffer, because already these blocks are buffered, so transmitter can retransmit it. You are now saving the resources. Basically, instead of retransmitting the entire transport block, you're kind of transmitting only the specific block that is failed. That's the advantage of this approach. But for this, there is a disadvantage also. When you have to report group level, transport block level ARC NAC, it is just 1 bit. It is enough for code word or one transport block. But here, you require it for each code block. If the data is huge and when GNodeB decided to convert the transport block into 10 blocks, sub blocks, divided into 5 block groups, for example, like in this case, now you at least need to give the mobile equipment permission to send totally 6 bits of ARC information. 1 bit is for the kind of transport block. Actually, transport block level not needed. 5 bits are enough. In these 5 bits, this group you report 1, this group you report 1, this group you report 0, this group you report 1 and 1. Kind of giving a hint to GNodeB that definitely transport block is failed because of these middle blocks. That's the idea. So PUCCH carrying size will increase. Is this clear? Everyone understood? Any questions? Okay. Now the next part in the PUCCH is called a scheduling request. So what would be there in this scheduling request? First of all, why this scheduling request is? In NR, there are multiple ways of requesting for uplink resources. Buffer status report, scheduling request on PUCCH, random access procedure. Now, I'm kind of giving you a question for you to participate. By explaining some basic concept. So listen carefully. Buffer status report is sent by MAC layer. I mean to say, mobile equipment's MAC layer to GNodeB's MAC layer. This buffer status report would be sent. This scheduling request, as I told you, is sent on PUCCH. It's done by physical layer. Random access procedure is done on a special channel called as PRACH. Now, all the hints are here in the particular slide that are required for answering the question that I'm going to ask. In which case you go for PRACH? In which case we go for sending this buffer status report or scheduling request on PUCCH? So that's my question. All the inputs needed are here. With the help of the information from previous class, you can guess and tell me the answer for it. So I'm kind of expecting a reply from you guys now. Okay, 5 of you. Once again, the question, when do we send random access procedure? When do you send buffer status report or schedule request on PUCCH to request further resources. What was the segregation? When do we do it? PRACH must be in uplink. PRACH is uplink. Everything is uplink. All the three are uplink here. RACH will be used for synchronization. Of course, RACH not only would be used for synchronization. One of the things that is inherently happening inside RACH procedure is synchronization, because the timing advance information is being provided. But in the random access response, you are having PUSCH resources as well, the uplink resources as well allocated to you. If you remember the RAR, that information is kind of present in it. Any other answers? Come on, guys. At least some participation. Come on. I was kind of given an instruction, a clear instruction that I must engage you somehow. I cannot deliver in a monotonous tone continuously.
Sir, buffer status report MAC sent to physical layer.
Mm-hmm.
When it gave the status report how much data it have to transfer.
Okay. I'll give you one more hint. At least on the basis of this hint, you must be able to answer. If a mobile want uplink resources, it can send a buffer status report. This buffer status report is kind of sent on a channel called as PUSCH. This scheduling request is sent on this channel called as PUCCH. Random access procedure is done on a channel called as PRACH. Now you can tell me. I told you one more hint. PUSCH, PUCCH, PRACH. So what you have to look for? What am I giving as the hint here, and what are you looking here for? Why I told you that channel names there? What is the purpose of channel names? Is what you have to look for. What are these channels indicating you or telling you? And again, PRACH is not only for sync. PRACH can be used for resource requesting as well, uplink resource requesting also. Now I'm asking you, the question is different here. I'm not telling you what is PRACH for. PRACH is used for sync, PRACH is used for uplink resources. I have put down here 3 different mechanisms of requesting for the radio resources for uplink direction, which mobile can request it from GNodeB. I'm asking you, when does mobile send which one?
The scheduling request is sent when UE wants to send some data. At that time, it will ask for uplink resources.
Someone answered RACH is for initial access. RACH is for initial access. Okay, that is correct. See, all these things are correct statements that you guys are making. That PRACH is used for sync or PRACH is used for initial access and so on. But that's not is the answer that I'm expecting. When I tell you the answer, you will understand what do I mean by that question. You will get the logic behind that question. Okay, but at least I'm making you Think about it. Okay. Now, if I tell you the answer, I am guaranteed that you won't forget it. Now, this is the answer. What am I expecting from you as the answer? These two channels, PUSCH and PUCCH, are allocation-based channels. That means mobile is allowed to use PUSCH or PUCCH only when they are allocated, when the resources are allocated on any of these two channels. Whereas on the other hand, the PRAT channel is a random channel whose resource information is provided as part of system information, and any mobile is allowed to use the PRAT at any time. Now, what is the answer that I'm expecting after explaining that property? When do you use which method to request for uplink resources? When you have PUSCH resources available, you can send buffer status report. By doing that, you can request for the uplink resources. When you don't have PUSCH resources available, you have only PUCCH resources available because these two are allocation based. You have only PUCCH resources available. You have to request the resources by using this scheduling request, 1-bit scheduling request. If both of them are not available, you don't have PUSCH available, don't have PUCCH available, then you have to do PRAT. Obviously, all your answers are correct. Somebody told that PRAT is used for initial access. Yes, because PRAT is indeed used for initial access, because during initial access, you don't have PUSCH and PUCCH allocated, available. They are not allocated to you. They are not available for you yet. What is the kind of linking between them? How do we link them up and how do we kind of relate them? If you are sending a buffer status report on PUSCH, maybe you have resources available for the present PUSCH transmission, but you are kind of seeking the resources for the future aspects. Like you have some more data waiting in the buffer. Whatever the data that is arrived earlier, you may be packing and you are sending. At the same time, you are sending a buffer status report to the GNodeB, asking that, hey, for my future, I need more PUSCH resources. That means by using PUSCH itself, you are complaining that I need more PUSCH resources in the coming up time units, in the coming up slots. Please allocate me. But when you don't have even PUSCH available, for some reason, PUSCH resources are not available, even though you are in connected state. Because maybe you are quite mum, you are not doing anything. Network did not allocate you PUSCH resources as you don't have anything to transmit. But suddenly you have some data is ready to be transmitted. So then you cannot request it by sending buffer status report, because to send buffer status report, you need to have PUSCH resources available, but they are not there with you. But somehow these PUCCH resources are kind of configured in a repetitive manner. Like you are allowed to use this PUCCH once in a while, every X amount of time in a repetitive fashion, as long as you are in connected state or as long as the network wants you to do that. It will give you a chance to use this PUCCH to send this scheduling request at least every now and then. But if that resource is available, if the PUCCH resource to send this scheduling request is available, if suddenly you required of uplink resources for dispatching your uplink traffic, immediately what do we start is this scheduling request procedure. On PUCCH, we send this scheduling request on PUCCH channel because we have that opportunity now. When we don't have these both things available, PUSCH and PUCCH not available, we consider that mobile equipment is coming from either idle state or doing initial access, or it is coming out from a state like radio link failure or some other failure problems. When such kind of failures occur, you cannot come back and freely use PUSCH or PUCCH, or if you don't even have the resources allocated and this is the initial access you are doing, you don't have a choice but to go for PRACH. That is the only option that is available for you. You have to perform random access procedure. Because you are allowed to use this random access channel anytime you want. Is that clear? Am I clear in this right now? Have you understood?
Yes, sir.
Yes. Buffer status report and scheduling request is done in connected state for the mobile, who is already connected with the Gnode B, kind of coordinating with the Gnode B. Either you have PUSCH resources available or PUCCH resources available. So you can send a notification to network or Gnode B that I need resources by using these channels. If you don't have them, only way that you can achieve that is by doing random access procedure. But while performing random access procedure, you are coming up just now and you wanted to request for the resources, uplink resources. For you, PUSCH resources will be given. But to transmit PUSCH, you need to have the correct timing adjustment, which we call it as sync. That is why what they have done is on this PRACH channel, they have merged these two techniques. So PRACH is used for requesting radio resources. At the same time, it would be used for the synchronization. Gnode will be able to guess your timing estimate and it will provide you the proper timing advance value so that you will be perfectly transmitting PUSCH. Both the things would be happening. It's like two birds for one stone kind of stuff. See, the point here is you have to deeply understand like why one particular thing is taking place. You should not be like looking on the surface of it and say, okay, PRACH is used for initial access. That is what is written in the specifications and we have to do it. But why? When you ask that question, you will go into these deeper answers. Because PRACH is common resources. What is the meaning of common resources? Which are allowed to be used by any subscriber. Any subscriber don't need any Gnode B's permission to use PRACH. But you require Gnode B's permission to use either PUSCH or PUCCH. Because they're allocation based. Okay, so now from here we get the hint that for this PUCCH, repetitive resources will be provided irrespective of whether mobile equipment would be using that scheduling request or not. Okay, or would be using this PUCCH or not. For every subscriber who is in connected state, network will provide the opportunity to transmit PUCCH as long as they are in connected state. But PUSCH resources would be provided only on the need basis when you have to transmit something in uplink direction, usually traffic. Where by pulling huge amount of data from the higher layers, you pack it into a transport block and wanted to send it. That time you use the PUSCH. But even when there is no data going on in uplink, every now and then mobile equipment have to use PUCCH. Why? There are multiple reasons for it. One reason is if suddenly uplink data is generated by your mobile, to request for uplink resources, you may need it. Okay, that's one reason. Second reason, you are not doing anything in uplink. Uplink activity is kind of zero. Network is not allocating you any PUSCH resources. But network still need to allocate you PUCCH resources. What is the reason? Because network is sending you huge amount of traffic for you in downlink. Now, if the traffic is arriving in downlink, for the traffic that is coming in downlink, definitely ACNAC should go in uplink. So every now and then mobile need to send acknowledgement or a negative acknowledgement in uplink for that. For the data that is coming in downlink on PDSCH channel. So even though there is no traffic in uplink, but still you are needed to use PUCCH for transmitting this ACNACs. Because this PUCCH channel is designed to be repetitive and some amount of fixed resources, repetitive resources are getting allocated to the subscriber for the use of this channel. What they decided is, hey, we must be able to make the mobile equipment use this channel for various purposes. So depending on the present need at that particular point in time, mobile would transmit the corresponding information. For example, we are designing one channel which is having repetitive resources. So at times mobile need to send scheduling request. At times mobile may need to send ACNAC for the data that is received in downlink. At times mobile may need to send CSI reports for the downlink operation that is going on, downlink MIMO operation that is going on. Uplink may not be happening, uplink nothing may be happening, but you have to send CSI reports which are requested by the network. So you are sending CSI report. So for all these general purposes, to achieve the lower level control, physical level control, we are using this, PUCCH. So they have merged and put everything together into this one channel, because this has got repetitive resources. Mobile can use it for any purpose, but when it is sent, network and mobile equipment have to kind of coordinate what information is being sent, and all that need to be indicated intelligently. It would be indicated and it would be sent accordingly. So there are a lot of internal structures created for it. But because you are not going to develop the physical layer aspects, I'm not going into those internal structures. But I'm giving you the concept there. So based on it, the receiving entity would be able to determine what kind of information is sent by UE on various situations. And then take that information and use it for apply it for the current operation that is going on, depending on what kind of information is received. If it is ACNAC, you decide what to do with the previous transport block that is waiting in the buffer, in the transmission buffer. If you receive a ACK, the transmitter throws that into dustbin. If you receive a NAC, you know that you have to keep it till you get an acknowledgement. So you have to keep it. So the next action is decided based on the information reported. Next thing, if you have sent a scheduling request, physical layer receives it. G0B's physical layer kind of need to send the scheduling request to MAC layer, because MAC layer is the resource allocator. MAC is the one who allocates radio resources or your PRBs, physical resource blocks, for the subscribers for uplink operation. So that is the course of action that physical layer takes, provides the scheduling request received from the mobile to MAC layer. But if the CSI report is received, use that CSI report, apply that CSI report that is received, and decide the next steps, like what should be the pre-coding matrix that you should use for the next downlink transmission. Or if the CQI is reported as good, you decide to, you report that CQI value to MAC layer. MAC layer kind of decides based on the CQI value reported what should be the scheduling and what modulation should be used, etc. Those factors will be decided at the time of scheduling. So all the information that is going in here on this PUCCH channel is kind of determining various activities that are going to take place in the next steps. Is that clear, guys? Any questions on it? Okay. Next, reference signals. We have two different kinds of reference signals, sounding reference signal and CSIRS reference signal. First, sounding reference signal. It is uplink only signal and it is used in TDD mode. The idea is you make mobile equipment to transmit the sounding reference signal by allocating some particular resources for it, which of course is conveyed to the mobile equipment, where and all, in which and all symbols it can transmit this SRS reference signals, which are calculated again by scrambling sequence, QPSK modulation. Everything is the same. I've decided not to show even those things removed. But why it is only applicable for TDD mode? and what is the logic behind it. And this SRS is also used, is kind of a reference signal. It is called as, reciprocity based reference signals. The idea behind it, or the meaning of that, is that in TDD, we are using a single frequency. Whether mobile equipment is transmitting the frequency to the G-Node B or G-Node B transmitting the frequency to the mobile, it is the same frequency. When there is same frequency, the channel conditions are kind of similar, either in downlink or uplink, because the signal path would be the same. From mobile to G-Node B or G-Node B to mobile, exactly it is the same path. For the signal. So, they thought that, hey, this SRS kind of can be helpful for the G-Node B itself to decide the CSI information for downlink. So that means mobile equipment exclusively not required to report CSI in uplink by using the PUCCH channel. If we are using sounding reference signal, if sounding reference signal is perfectly working, you don't need to measure the channel state information neither by using SSB block nor by using CSIRS signals. Simply, you can transmit SRS, sounding reference signal, in uplink. By receiving the sounding reference signal, G-Node B itself can estimate what are the CSI factors that will be applicable for the subscriber. It can estimate the CSI factors on his own. So what is the advantage of using the SRS? You don't you do not require to calculate this channel state information and send it. You means mobile equipment. Exclusively, you don't need to report the CSI every now and then. Not needed. So you can ignore CSI. Actually, in TDD mode, CSIRS might be absent. It would be completely absent. It won't be there. So if mobile equipment have to measure the signal strength, it will either use the SSB typically for measuring the signal strength if CSIRS is not there. The idea behind this is because the channel conditions in uplink and downlink are same for TDD, as it is the same frequency that both mobile and G-Node B are transmitting. Whether G-Node B, for example, if we make SRS gets transmitted from G-Node B, what do we need to do? G-Node B transmits it, mobile receives this sounding reference signal. From that, it will estimate the CSI values. But that CSI values that mobile estimated is equal to, if we make the mobile transmit SRS, G-Node B calculate the CSI and compare the CSI values with the CSI values reported from the mobile, both would be nearby, almost same, because the channel conditions are same. So mobile don't need to report CQI also, channel quality indicator. G-Node B can estimate. The sounding references signal is going to make the things much better for G-Node B side scheduling. Because G-Node B can estimate everything related to the subscriber on the basis of this SRS easily. But if this is a FDD operation, we would be using this CSIRS. Where your uplink channel conditions and downlink channel conditions are different. So if mobile will have to estimate the CSI values for the downlink MIMO matrix that G-Node we need to apply, for which mobile need to estimate the channel conditions in downlink. If you make the mobile equipment transmit the signal in the uplink, G-Node we won't be able to calculate. Why not? Because the frequency is different. Uplink frequency is different. Downlink frequency is different. Channel conditions are different for different frequencies, because you don't know. But for the frequency that you are receiving in downlink, there may be huge interference. For the frequency that you are transmitting in uplink, there may be no interference in case of FDD. So if we make the mobile equipment transmit the signal, that cannot be used as a perfect method for the GNODB to estimate the things. So GNODB need to transmit the signal in downlink because mobile is supposed to estimate the channel conditions for downlink, for the downlink transmissions or downlink MIMO. So mobile sends the CSI for downlink MIMO. So what does mobile do? Mobile estimates the CSI and packs this information on the PUCCH and send it back to the GNODB in the form of PUCCH or either on the PUSCH if chance given. So the CSIRS not only would be used for channel state information calculations, it can be used for RSRP, RSRQ, and SANR, received signal, reference signal received power, reference signal received quantity, quality, and SANR is your signal to interference and noise ratio. So you can estimate even that. And the CSIRS signals would also be helpful for the mobile equipment to do the frequency and time tracking. How that is? The CSIRS signal positions are kind of decided on the cell scrambling code. Your scrambling code changes in a cell, the position of the CSIRS would be different. They would be changing as well. That means that in different cells in the adjacent locations, CSIRS signals would be placed at different places, different positions. Of that kind of, that technique that went in behind it. They wanted to place it different places, the CSIRS signals from different cells. So mobile can estimate whether it is perfectly in frequency sync or time sync in the frequency domain, and you can estimate whether whatever the subcarriers you are thinking there, are they the same subcarriers, are they different? If you estimated your subcarriers and everything wrongly, you won't be able to receive CSIRS because wherever you are expecting CSIRS, there won't be any CSIRS symbols there if your synchronization gone wrong or your time synchronization gone wrong. So mobile would be using the CSIRS kind of every time syncing with the radio frame, identify exactly which subframe, which slot, where, what is going on right now. Even if some amount of time delay is created because mobile is traveling at very high speeds and kind of created the radio frame related sync issues, those sync issues can be solved by using the CSIRS that is getting transmitted from the network. Of course, the CSIRS, we can use it for beam management. I already told you how earlier in our previous slides. But now you can create, the CSIRS can be antenna specific. If you are using 4 antennas to transmit CSIRS, you would be transmitting CSIRS in different positions in different antennas in MIMO scenarios, which will help mobile equipment to estimate the channel conditions for each antenna specific path or signal separately, instead of estimating it for only one CSIRS coming from one antenna. That's kind of needed. So you need to send the CSIRS signals in all the antenna symbol positions. If you have 4 antennas, you have 4 frames, 4 radio frames, or from 4 grids. In that grid, some locations would be occupied by CSIRS. But what I am telling you, if you are using 4 antennas in downlink, all the antennas might be containing CSIRS signals, but at different locations, different positions, not conflicting with each other. Non-conflicting positions, they'll have the CSIRS placed, so that mobile would be able to estimate the path-specific channel state information specific to that antenna, and that information only it will convert it as matrix. Because from each antenna, your channel condition or channel propagation would be different. From each antenna to your each antenna, it would be different. So to estimate that, CSIRS must be antenna specific. And CSIRS configurations can be periodic, semi-persistent, aperiodic, etc. There are various possibilities of configuring it. I'm not going into those deeper details, but later, anyway, the CSIRS and this SRS are not finished. We'll again hit in MAC. I'll add more information at that time. I'm just giving you the brief description at this stage. But this is heavily linked with MAC layer. So one last thing that we could do in uplink is to look at uplink DCA format, just like how we have looked at the downlink DCA earlier. For a PDSCH scheduling operation, we have studied DCA 1.0. When you receive a downlink control information on the PDCCH channel with the 1.0, you know that one PDSCH code word is kind of allocated for you, where you have to download it. To know it, you read DCA 1.0. But when you are reading DCA 0.0, that is for uplink scheduling. So when you have uplink scheduling, what kind of information would be available? Similar information like downlink. What kind of DCA format you are receiving, that one bit will indicate out of multiple DCA formats, which format you have received. Then what is your frequency domain resource, which kind of tell you which resource blocks are part of which bandwidth part. What is your time domain resource? And whether the frequency hopping is enabled or disabled. What is frequency hopping? I already explained you whether you are going to transmit all your resource blocks continuously on the same frequency level, or you would be continuously changing your frequency from one subband to another subband to another subband to escape from this frequency selective fading. Modulation and coding scheme. This logic is the same as the downlink. We have studied that. The MCS value table runs from 0 to 31. That kind of tells you what modulation you should use for your uplink operation and what it should be the coding rate. We saw the table in our previous session. New data indicator. New data indicator tells you, it stands for NDI, new data indicator. This NDI is used to explain the mobile whether it will have to transmit new data or the old data itself, repeated, retransmission related to that. Remember, I have explained you this few slides back. For downlink traffic, you have to exclusively send ACK or NAC in uplink on this channel called as PUCCH. But for uplink traffic, once you send the uplink traffic on PUSCH, when the next PUSCH resources are getting scheduled on DCI format 0.0, it will be conveyed to you whether you are going to transmit the same transport block that you transmitted earlier or a new one. Based on it, you will decide the next step. So this information is coming in downlink control channel in the DCI format along with your data scheduling. Redundancy version, the possible values are again 0 to 3, 2 bits. So each number would tell. So 0 means redundancy version 0. And 1, 2, 3 can typically be used when the MCS index values are 29, 30, and 31 during retransmission. So which redundancy versions, which set of coded bits you want, which version of coded bits you want for incremental redundancy. HARP process number and TPC command, transmit power command to do the power control in uplink for uplink channels. This power control is a very heavy topic, and there is a relationship with this power control in the MAC layer. So we will again study at that time during one place, all at one place I'll introduce. And for the mobile, whether uplink, normal uplink is enabled or supplementary uplink is enabled. Basically, it represents whether supplementary uplink configured or not configured. 0 means not configured, 1 means supplementary uplink is configured. We discussed about this supplementary uplink concept, but we don't go any further than that. That's the kind of end of it. So with that, we have covered the basics of the physical layer, completely finished with that. So to summarize, exclusively here, about what we have studied in the physical layer. So we have two segregations, downlink and uplink, two parts. So first we have looked in downlink part. In downlink, what we did first, we studied, first we understood about the modulation mechanism, where we have studied the BPSK, QPSK things, and how the data would be represented in terms of symbols. Then next we have studied about multi-carrier transmission, or we simply call it as the OFDM, orthogonal frequency division multiplexing, which is also known as multi-carrier transmission. What is the difference between single carrier transmission and multi-carrier transmission? In multi-carrier transmission, we learned that every carrier is going to be associated with a different frequency when the symbols are getting converted from frequency domain to time domain samples, and all those time domain samples will be multiplexed, muxed, and that single output vector, whatever is created, that single output vector we transmit on the carrier wave. Then we started learning about the resource grid, where we have introduced the time domain and the frequency domain. In time domain, we have the symbols placed across the time. In frequency domain, we have subcarriers. How many subcarriers are there dependent on your U value. So we learned that. Okay, next. Next, we have studied the PBCH, or we can say SSB block. In that, we have studied everything together. How the downlink synchronization happens with the help of the PSS, SSS channels. And also, we have studied PBCH and also its DMRS, demodulation reference signal, that would be sent along with PBCH in some particular symbol locations of PBCH itself. We carry DMRS. Then we have looked at the PDSCH. Then we have looked at PDCCH. So PDSCH carries the data. What is the total data process that will take through? Of course, in the middle, we have, after this, before resource grid and everything, we have studied this MIMO part also. I missed that. MIMO beamforming part. So I studied PDSCH, PDCCH channels. PDSCH is used for data transmission, PDCCH used for sending control information. Then in the middle, we have introduced the CSARS, the reference signals, and also we have introduced something called as phase tracking reference signals, which is a modified version of CSARS to do the phase tracking and travels along with the PDSCH. So we have studied this much. In uplink, we started with PRACH, or RAR procedure, random access procedure. Then today we have seen PUSCH, which is a similar channel like PDSCH, which can carry the data, for which scheduling should be done. For PDSCH, also scheduling would be done. PDCCH, only PDCCH scheduling is not needed. Mobile equipment can listen to PDCCH anytime in the downlink. But for that, mobile equipment should know where the PDCCH resources are located. And that information is conveyed to the mobile in the form of scheduling system information, in the form of PDCCH core sets, where those core sets are located, and the set spaces, etc. All related to all those things, you get the system information. From that, mobile know where PDCCH is located. It can download. It can find out whether on the PDCCH its own RNTI is scrambled or not. CRC is scrambled with its RNTI or not. Based on it, it can decide whether the PDCCH is for him or not. But when it comes to PUSCH, it should be based on scheduling, uplink resources that are scheduled for you. Similarly, PUCCH also is scheduling based. You cannot use it just like PDCCH. PDCCH is for all, everyone. Anyone can get the data on PDCCH because it is carrying scheduling information for many subscribers. And each subscriber's information is called as DCI, which is kind of scrambled with their respective RNTI values. But whereas the PUCCH carries one particular subscriber's experience, one mobile's experience in the network, how it is feeling about the present live situation related to ACK, NACs, and it want any new uplink resources for PUSCH, or what is its CSI information, etc. All these things can be kind of sent on this PUCCH. But it is scheduling based. Now this SSB block is common. It's for everyone, on which anybody can download this SSB block and decode the PSS, SSS, and then subsequently the PBCH and PBCH based DMRS. PDSCH is different. I will explain. PDSCH can be used for all. It can be used for many. It can be used for one. All possible combinations are available for PDSCH. We will study that a little later. But PUSCH specifically for one subscriber, whoever gets it allocated, who gets it scheduled. PUCCH is also for one subscriber, whoever gets it allocated. Along with PUSCH, there is DMRS. I decided to ignore, just like the PDSCH DMRS, because I already introduced. I decided to ignore that. For PUCCH also we have DMRS, demodulation reference signal. I decided to ignore even that. So they will be traveling along with those specific channels to help the GNode be easily decode or easily successfully decode SCH and PUCCH channels. Then today we introduce the difference between SRS, that is transmitted in uplink, and the CSIRS, which is transmitted in downlink, the special kind of reference signals. But whatever the CSIRS that is transmitted in downlink, by estimating that CSIRS, we would be sending the CSI on PUCCH. So that is how these channels are interlinked. CSIRS comes in downlink. By listening and estimating, mobile equipment would they have to transmit CSI, but to transmit CSI we use PUCCH. That's how they are linked. SRS is used for your channel state, sounding reference signal. It is called as. It is used for CSI estimations at GNode B without mobile having to provide it, because the channel conditions are same in the 3DD case for both uplink and downlink. Is this clear, everyone? I might have missed certain things, but I tried to summarize as much as I could. We take a break for 10 minutes, 11:40 now, 11:50 we come back, and we will continue with our next protocol layers. And after that, we are going to have some kind of a little test on the physical layer. Okay, so to see where are you at. Okay, let us come back in 10 minutes time.